I just want to discuss some of the questions. So, was everyone able to get this? Huh? Yeah. What is the result you got? Everyone was able to get this? C1 minus C2 by CF? You?
Sir, tell me how to do it in Integrator.
Okay, let's.
The assignment question that
Yeah, let's do it. I mean, at least by charge conservation, let's. Okay, you're able to get it? What did you get? Okay. See, intuitively speaking, see, basically have this is something you know already, right? This is simply existing to take out charges from these capacitors. You just need to see what are the charges getting transferred. If you look at C1 alone, let's not consider this. So C1, what happens in phase 1? We are charging it to VDD, right? So in phase 1, it is charged to VDD in this polarity. So the charges stored in this plate is what? Yeah, minus C1 VDD. In phase 2, we are grounding this, and it's connected to the virtual ground. So the charges settled here is, so here it is plus C1 VDD. Now if you look at C2, so C2 in one phase it's completely discharged, right? In the other phase we are directly connecting it. This is similar to the delay-free switch cap amplifier, right? In one phase we are resetting, in the other phase we are directly, basically sampling and charge transfer happens in the same clock phase, like this. Okay, and this has to be charged to, in this polarity it has to be charged to C2 times VDD, and this charge has to come from VDD, and that goes here. The difference is, in the first case, when we are doing it, C1 was doing this. So the charges that reach C2 is coming from this capacitor. Now for C2, we have something like this. This is VDD. So who is supplying the charge now? The supply is supplying the charge, and that is plus C2 VDD. So basically you get the same thing. Here it's minus C2 VDD. And in fact, this is how we normally sense, this capacitors. Most of the sensors, this gyroscope sensors or touch, everything is a capacitive sensor. You have to sense very small changes in capacitance, and this is how it is done. Usually, you have some differential thing like this. In this case, let us say, depending on the acceleration stuff, ideally both of them will be same. Let us say, depending on the acceleration, the capacitance value will change, and this is one way in which you can convert the capacitance to voltage.
In a general question, we cannot apply charge conversion at the Vout without.
Yeah, because this is again like KCL, right? You can't apply KCL at this node until you know the current here.
Yeah.
And it is not relevant. The point of applying KCL at any node is to find that node voltage. The voltage source is fixing this voltage to, let's say if this is Vx minus A times Vx or something. So there is no point in applying KCL at output of any voltage source. Right? I think the second question was here, right? Yeah, this was the second question. What was let's say if the op amp has no offset and it's ideal, what is the output you get? V in.
In the first phase, V out at 20, so
that's okay. This is so V out at, in the first phase it's doing this. I'm asking only at the end of phi 2, right? In first phase, let's do it. In first phase, we have what? Sorry.
the first phase, the estimate will be out.
That's okay. First phase, it will be not V out hat, right? It will be, if the op amp is ideal. Let's say first the op amp is ideal. 0. Right? I'm asking, this is in phi 1, I'm asking only in phi 2, right? In phi 2, what we are doing is we are basically putting this capacitor across the op amp like this. This is again the same logic. We want to process the charge or the voltage stored across capacitor, but we don't want to draw any current from the capacitor. So we make sure that the current is supplied by the op amp, and the output of the op amp must be equal to the voltage stored. So you connect it in negative feedback like this. This is how we also came up with the switch cap amplifier, right? So if you have any capacitor charged to something, you want to process the voltage or the charge stored across it, but you don't want to draw any current. So you put something here, right? And the reasoning was, if this has to be V, let's say if this is charged to V in, if you want this to be exactly V in, this must be ground. but you can't connect it to ground because then you lose out the charge. So you put it in, you connect this to a virtual ground, and that is where you need the op-amp. This is the same as that. In fact, this is called a flip around sample and hold, or flip around track and hold. Because in one phase you are sampling it, in the other phase you are sort of flipping the capacitor and putting it in feedback. And the reason we are doing this kind of configuration is, I mean, you could as well sample the input across the capacitor like this and then put it in feedback. But why are we doing it like this? Why are we sampling the input in this manner? What is the advantage? I mean, we are sampling the input, negative is connected to the virtual ground, right? So what are we trying to achieve here? I mean, if it's an ideal op-amp, it is all okay. But in case of practical op-amp, will this help anything? Okay, the question is. Yeah, see, the question is, you could as well charge the capacitor like this, and then put the capacitor in feedback. Yeah. Now, if what we are doing instead is we are sampling it like this, and then putting it in feedback across the capacitor like this. If I do it properly, yeah, that's okay. You can draw it like this. And remember that the reason we are sampling with respect to the virtual ground is the virtual ground is a sacred node which contains information about all op-amp non-idealities. So in this case, if this has an offset, if the gain is infinity, this will also be offset. And if the gain is not infinity, you can work out if this gain is A, if this is Vx, what will be Vx?
VOS minus V out by.
No.
Yeah, okay. It will be VOS upon A, 1 upon A.
It's
A into VOS upon 1 plus.
It's basically A by A plus 1 times VOS.
Yes.
Fine, you can work out, right? This is basically V out, I mean, this is also Vx. Vx is A times the non-inverting terminal minus the inverting terminal, you get this. So in the other phase, this is V out. You still have the offset. What will be this voltage?
VOS minus V out by A.
Yeah, again you can write it. V out is basically A times the non-inverting terminal minus the inverting terminal. So this will be minus V out by A plus VOS. Once you know this, you can start, I mean, you can just put charge conservation and you should be able to get it.
Answer is V into A upon.
See, ideally you should get V in and the offset should not be present. Now with finite gain, I mean, if the gain is infinity, you get V in. If the gain is some A, what is the output you should expect?
V into A.
I mean, this logically speaking, right?
A upon 1 plus A.
It makes sense, it should be of this form.
Yeah.
Now if the gain is infinity, there will be no offset. If the gain is finite, you will get something like A plus 1. I think here you get something like this. Something like this. Okay. So let's look at some more questions maybe. What is other stuff? Yeah, maybe first one. Yeah, I guess this is, what is this guy? What circuit is this? You are sampling in and feeding it to the, what operation?
Z inverse of 1 plus.
This is an integrator, and the only difference is the sign will be negative here, right? Because here we are transferring the positive charges to this plate, so this will become negative. Whereas here the sign will be flipped because here we are transferring charges from the bottom plate here. And in this, I had asked you to consider parasitic capacitors, right? Because in practice, when you have a capacitor, you always have, I'll draw it like this. This is the bottom plate. You will have two parasitic capacitors on either plates. So again, I'll not work out completely. So which of the circuits is better?
What is better? There was no effect of it on that.
I mean, simply logically speaking, here, if you see, you will have parasitic capacitors both here and here. The parasitic capacitor at the bottom plate is not a problem because that's grounded. And the top plate capacitor simply adds to C. So whatever transfer function you had, that will be C plus Cp, right? Whereas here, if you see, you do have two parasitic capacitors.
Except for C2, there will be no effect, right?
Yeah, C2 will have no effect.
C2 have been grounded, this will be.
Yeah. For C2 again, ideal op amp, this is ground, no issues. and this is the output of a voltage source. You connect anything, you put an elephant there, it will be fine, right? So yeah, in the second thing again you have parasitic capacitors, these two guys, but in one phase this is grounded, in the other phase, so that way you will not have an effect. Okay? So in fact that's why this is called parasitic sensitive integrator, and this is parasitic insensitive integrator.
So that capacitor will be grounded in both the phase 1 and 2.
Which one? For C2.
Not C2. This C1, the right one.
Ah,
That will be grounded in both the phase.
correct,
No
correct.
one
Yeah,
also.
yeah. So this is parasitic insensitive. And if you actually think about it, we started with a simple sampling circuit like this, and then we finally decided to do something like this. What was the motivation to do this? What was the motivation to do this? What was the issue we saw with this simple?
So the charge was.
The charge injection was there, and that's why we decided to do bottom plate sampling by turning this off early. Now doing this thing also helps with this parasitic. So it has two advantages. Yeah, this I think it's okay. Yeah, so this one, how do you do it? You can copy paste this. Ah.
1 minus Z. Sorry, 1 plus Z inverse by 1 plus Z.
I think that, what did you say? What? 1 plus?
1 plus Z inverse by 1 plus Z inverse.
I think that is not right. Okay, again, you can do by charge conservation, but I'll just say how we can do it qualitatively, right? See, you see the circuit. Is there something that is familiar to you in this? Is there something that is looking familiar to you?
The down circuit is coming.
What is this?
The down circuit.
It's an integrator, delayed integrator. Again, if I try to write it as a block diagram, we have this guy. And remember, the output sampled at the end of phi 1 is this. And what we are doing here?
We are charging the capacitor.
This is V out, let's say.
But then we are not using it anywhere.
We are using it, right? What are we doing here? In phase phi 1, we are resetting it.
So I have blocked that whole block, that capacitor, upper capacitor and the middle capacitor, that will be a non-delayed integrator.
Correct. See, if you think about it, assume that this is another input, right? For now, some V. If you look at this part of the circuit alone, that is also an integrator. But let's come to it whether it's delaying or non-delayed. This is also an integrator, right? Because you see that in one phase you are resetting, other phase you are directly sampling it and transferring it to the integrating capacitor, and that keeps getting integrated, right? So if I draw this, so if I remove this part alone, this is again an integrator, right? But you see what we are doing, we are only interested in the samples at the end of phi 1, right? No, if you see, right, we have already sampled in phi 1, right? What we are doing, in one phase we are resetting it, in the other phase we are transferring it, but we are only sampling it in phi 1. See, this is basically fed back like this, right? Okay. Now note that output is available in phi 1, right? In phi 1 we are not doing anything to this guy, we are resetting it. In phi 2 is when we are connecting it to the integrating capacitor, and it's again,
One getting the information.
so it's again, there is a delay. This is also a delayed integrator, because if you think about it, output is sampled in phi 1, it is only integrated in phi 2, but again it's getting sampled in phi 1. If I were to sample this in phi 2, there is no delay. Okay, so if you think about it, what's happening here is we have this guy. We are basically subtracting the output and doing it like this. Loosely speaking, that's what is happening, right? And remember that, I mean, there is a negative here, because when I do this kind of delay-free business, I'll have sign inversion. I mean, remember that if I sample in one phase and then pass it on, the charges from the bottom plate is what will get transferred, so this will be plus. But if I do a delay free operation like this, the charges will be coming from the voltage source, that will be plus some Q, so this will be plus Q, this will be negative. And since the feedback is doing it in delay free, you will have a negative, and this is what it is. And of course, you can put charge conservation, and you should also be able to find that out. So yeah, so here what's happening? I mean, you have again two paths. What is happening in this path? No, it's not 1 cycle delay. Look carefully, right? So we are sampling the signal in one phase. In the second phase, we are transferring this to another capacitor. But this capacitor already had some previous information. To the existing previous voltage, we are adding the input. It is some kind of integration. So if you think about it, in one phase I am sampling the input. Now I am drawing it only for this guy. Okay. This is in phase 1. In phase 2, we are basically going and connecting these two guys in parallel. Right? So in phase 2, if you see, this capacitor already has some voltage. We are sampling V in, let's say it's n-1. So right now what will happen, this capacitor already had, say, V out of n-1. So we'll have something V out of n-1 alpha plus some beta times V in of n-1. That will be a final output. Okay. And in fact, you can work out, let's quickly work out and see what will be the transfer function, right? So if I call it C1, C2, what will be the final output? We will have something related to V in of n-1 and something with V out of n-1. What is the ratio? For V in, what is the ratio? Right? If you write the transfer function, what do you get? I will get C1 by C1 plus C2. Right? So what does it remind you? What does this remind you? Does it remind you of any transfer function that we have seen in the course? Under some conditions, does it remind you of some other function? What? Yeah. It's an integrator. I mean, ideally this is the integrator, but now what we get is some, let's say, alpha z inverse by 1 minus, we get inverse. Okay, and let's say this is 1 minus alpha and this is alpha. If I actually look at the impulse response of this, that is, if I apply an impulse to this integrator, what will be the output? It will be a step. So you'll get. So what will be the impulse response for this guy? I mean, remember, if you are comfortable Fourier transform, in Fourier transform, this is looking like 1 minus alpha e power minus j omega. What is the Fourier transform of this guy? Okay, so I mean, let's think logically. This is basically impulse response, which is u of n. If I apply delta of n, it's an ideal integrator, we get u of n. And here we get u of n because this coefficient is 1. So now this is some other coefficient. So what do you think we might get? Not exactly. So you'll get alpha power n times u of n actually. And that will be looking like this, right? It will decay exponentially.
No rule of 1 minus alpha.
I mean, I'm ignoring this 1 minus alpha thing, right? I'm just taking this guy. This will be scaled by 1 minus alpha, of course. So in fact, this is called Lossy integrator. Because for an ideal integrator, you want the pole to be at z equal to 1, right? You want the pole at omega equal to 0 at DC. Whereas here you get the pole at some other frequency. Okay. And actually from here itself you can derive the actual ideal integrator. See here what we are doing, we are sampling the input in one phase and transferring it to another capacitor like this. And what we got was something like 1 minus C2 by C1 plus C2 Z inverse. I am looking only at the denominator, numerator we have something. So if this were to become 1 minus Z inverse in the denominator, what should happen? I mean, this factor must be close to 1. So how can you make it close to 1? What should I change? C2 must be really large, and in principle what should C2 be? If C2 tends to infinite, then you get an ideal integrator, right? Of course, you can't have infinitely large capacitor. We can try to make a very large capacitor. And what does it mean? So let's say you have a capacitor. So if I apply a test voltage, what will be the current drawn in Laplace domain? If this has a capacitance, the capacitor value C, what is the current drawn? No, in Laplace, yes, C times Vt, right? So now all I want is to mimic a large capacitor using a small capacitor, right? So this is the capacitor. So right now what I am doing is, bottom plate is grounded, and the top plate I am going and connecting my test voltage. If this capacitance is C, the current I am getting is SC times Vt of S. Now I want to make this really large. So let's say I want to make it S times 1000 C, right? So let's see what can we do. I mean, of course, this is a circuit. Test voltage is test voltage, you can't change. I don't want to change the capacitance value. I want to use only capacitance of C and get this somehow, right? And if you think about it, the bottom plate we are grounding, and the top plate we are connecting to test voltage. So this is something you cannot avoid. Looking here, you want to have a large capacitor. What is the other connection that we can change here? No, I don't want to add any capacitor, right? See here, the top plate I have connected to Vt. Right now, since I have connected the bottom plate to ground, the current drawn is this. So can I do something to the bottom side? So you have to get a current of this. This is the current I want. What should I connect here?
Minus 999
Vt. Is that fine? Yeah, now I have voltage Vt, I want to get a large value of Vt. What block does it? So you can basically take, this is like capacitor. So you take this guy, amplified with a large gain, put it here. So now if you look into this, it will look like the capacitance is amplified by a factor of what? No, if it's a gain of minus A, what is the factor? Yeah, 1 plus A. 1 plus A times C. It will look like a capacitance of 1 plus A times. And in fact, that's what we are doing, right? What we are doing, we are taking the opamp, doing it like this. Which one? Yeah, I mean, you can recognize it as the Miller effect actually, right? In fact, you can put any impedance here across a voltage amplifier with some gain, the impedance will get reduced. Okay, and this is what we have to do, and this is what we also did for our integrator, if you think about it. Of course, we came up to this circuit in a different way. This is another way in which you can obtain the same circuit. Okay. And okay, we don't have a lot of time, so let's do some random things. Yeah, and I mean, if you remember, when we looked at the history of the switch capacitor circuits, it all came about because we wanted to realize continuous time filters. But the problem with these was the time constants and all the center frequencies dependent on 1 by RC, and this product was not controlled. So we decided to mimic a resistor using a capacitor, and we basically did that by doing this. So if you have a resistor connected from a voltage source to ground, it is continuously draining charges from the voltage source to ground. With a capacitor, how can we mimic this action? So this is the voltage source. Again, the action is to dump charges from the voltage source and put it to ground. So in one phase we do this, right? And if this is V in, this is C. What is the average charge drawn by this guy in every clock cycle? What is the average charge drawn in one clock cycle? In one clock cycle, I am drawing a charge of CV in from the supply and putting it to ground. Let us say the clock period is Ts. What is the average current? CV in by Ts. I write as CV in Ts. So the average conductance. So that's going to be Fs times C. Yeah, and I mean sometimes people loosely say that the average resistance is 1 by Fsc, but that's not actually completely true. Simply because in this case, if you think about it, I have applied voltage as the input, right? I applied voltage as the input, I am measuring current as the output, and I am actually finding the conductance. Okay. To find the resistance, what should be the input I apply? What I should apply a current at the input that should come at the denominator and find the average voltage. And in this case, you will find that these two guys will not be inverses of each other. That's simply because we are not dealing with an LDA circuit. This is a periodically time varying network. The notion of impedance and admittance, they don't follow the inverses in this manner. And actually you can quickly verify it. So if you were to apply a current source as the input, do this, and you find the average voltage here, you will find that this will not give 1 by Fs. But as long as your two ends are fixed by two voltage sources and only you are interested in the average charge drawn or the average current drawn, then this equivalence holds good. And in our circuits, we are only interested in the charge drawn, so it's okay. And of course, yeah, these switch cap circuits were quite popular, but in the recent time, again, we no longer use switch cap circuits for designing filters as such. And the reason is this. So say you take any switch capacitor circuit, you have something like this, right? So the switch will have some finite on resistance, let us say. So in any circuit, we'll have something like this, right? Some opamp or some OTA driving this guy, right? Now let us say this is some V. Let's say the capacitor is initially uncharged. If I close the switch at this point, what is the current drawn here? Let's say the capacitor, at that instant we are drawing a current of V out by R on, and after that it will decay to 0, right? And ideally, how do you want this R on to be? Small or large? You want it to be really small, right? So this peak current can be really large, and this has to be delivered by the stage that is driving this. And if you look at high frequencies, Fs is going to be large, right? So which means the available time for sampling, that's going to reduce. If Ts reduces, what can you say about R on? The available time for settling reduces, so the on resistance that also has to reduce accordingly. So if this reduces, what can you say about the peak current? That will keep increasing. So this becomes unnecessarily power inefficient. So because of this, for general filters, we no longer use switch capacitor filters. We still go to continuous time filters. And in those filters, the problem was the variations in R's and C's. So that is usually tackled like this. So instead of having one R and one C, say you have a whole bunch of resistors and a whole bunch of capacitors. You can put switches here and connect appropriate number of them in parallel. Same you can do for the capacitors, right? So you can, that's okay. I mean, you can put a small capacitor here and put in parallel. Putting in parallel is easier than putting in series. We'll increase the capacitance. No, that's why you. No, it is not because of the chain C. Ideally, you want some R and some C. but instead you will get some r hat and c hat. Okay, so what you do is you put, instead of having just r here, let's say you can have some r naught, usually have binary weighted stuff like this. Okay, and let's say you have 4 r naught and so on. This r naught can be smaller or greater than your actual r. So you put a bunch of them in parallel. I mean, for a resistor case, it has to be much greater than r, right? You put a whole bunch of them in parallel so that this parallel combination approximates your required r. Similarly, for C, you have some C naught which is much less than C, and then you put a binary weighted capacitor structure like this, and put an appropriate number of them in parallel, so that this guy approximates the required value of capacitor C. And this just basically requires you to know what are the switches that needs to be turned on or off. So you can write a simple digital logic to work it out and fix it. That's what is done recently. So so the switch capacitor circuits, so you will find them usually you will find them used only in ADCs and in sensor circuits like this. For high frequency filters or generic analog filters, this is what we do. Some more time, 10-15 minutes let's take. Yeah, but of course people have also
But to realize these many resistors on the IC chip is completely inefficient.
yeah, it's not that inefficient, because let's say
Target is to reduce the number of, to eliminate resistors.
not completely.
Reduce the number of resistors. One of the design goals is also to use as minimum resistors.
Yeah, now there is a trade-off, right? That's what. Whether you want to burn so much power, if you use a switch capacitor, let's say you're doing a gigahertz filter, the on resistance will be really small. You will have to burn so much of power. So either you want to do that, and if you want to do that also, the opamps must be really sized large. So the transistor sizes will also increase here. Whereas on the other hand, here it's just passives. You can actually do it much better. So again, there is a trade-off, right? I mean, I'm not saying this is the only way to do. The trend is to do this now because it is much more power efficient and much more effective. But if you want really, really high precision at low frequencies, people will still use switch capacitor circuits. But of course, yeah, people have not stopped with switch cap circuits. So the issue here is the power consumption, right? And if you think about it, the current required is something like this. And we saw that if the bias current in the OTA is much smaller than this, what will happen? Yeah, we saw, right? If in the OTA, if the bias current is much smaller than the current demanded in the circuit, what will happen? Yeah, we had that slewing, and finally, because of slewing, what did we have? Yeah, we have something, but how does it impact? Correct. That is correct. You will have slowing, so you will not be able to match the current demanded by the circuit. Finally, what effect it has on the circuit performance? I mean, more importantly, I mean, in terms of circuit performance, I mean, like noise, something. What was it doing? If you think about it, what was the T slew? That was a function of the input. And we had something of the form e power T slew. So what does it? This straight away introduces nonlinearity, right? So you cannot have really small current here because that will introduce nonlinearity. So of course, one brute force way is to have the bias current to be much larger than the current demanded, but that's not efficient. So the usual practice is to have some current somewhere here so that it slews for some time, and that slewing is okay to meet your linearity specifications. But if you think about this case also, this is the current demanded in the circuit. You see that after some small time, the current required is almost zero, but still you are burning the same amount of power in the op-amp. That's terribly inefficient, and that has led people to look out for solutions where you can change the bias current of the op-amp also dynamically, because that is more efficient. So again, the goal is to have some kind of dynamic circuit where you don't consume high power all the time. You make sure the op-amp is able to drive the maximum current in the small portion of the time, and as time progresses you reduce the current in the op amp.
Okay, we do that.
Okay, let's see. So let's say take a simple this is a simple common source amplifier also, right? So let's say you apply VCM plus V in here. Here the current is always constant, right? But now as we saw, we want the maximum current only at t equal to 0, and then we want the current to reduce. So here the gate voltage is fixed. Current depends on what? VGS, to a large extent VGS. So if I want to reduce the current with time, my gate voltage is fixed. What is the only control I have? So I cannot completely connect it to ground, right? And so I should put something here, right? And if you see the element here, the source voltage must be 0 only at this point. At that point, if the source voltage is 0, the gate to source voltage is maximum, you get maximum current. But as time progresses, you want this voltage to increase or decrease? You want this voltage to increase with time. So now if you think about it, as current flows in the circuit, as current flows into that element, you want the voltage across the element to increase. What kind of element can do that? A capacitor. If you push in current through a capacitor, voltage across a capacitor will increase. So that basically then you can go and put a capacitor here. But remember that this capacitor should not always be connected. You first charge it to ground and put it, right? So you will have the capacitor connected in only one phase, say in phase phi 2, which is when you need the op amp. In the other phase, you connect it to ground. And of course, you can do a similar thing for the PMOS also. For the PMOS,
We can burn the power. We can keep I naught to be very large.
yeah, here the I naught is not fixed. I naught is dependent on the input. If you think about it, the initial current is basically dependent on the current in the transistor at VGS equal to whatever.
Not for this, in opamp.
We'll,
We'll do the current, so basically we'll do the same thing. In
yeah, that's what. I'm just talking for a simple common source, you can do something similar, right? So same you can do for PMOS also. So for a PMOS, what should I connect the source voltage to initially? It should be initially VDD, and as time progresses, the source voltage must decrease. So again, you put a capacitor. In one phase you do this, other phase you charge it to VDD. Okay. Now of course here you can put something PMOS or something here, but usually instead of putting some constant current source like this, even for a normal amplifier, right? If you have a simple common source amplifier like this, where you apply only the input here and connect it to some bias voltage to act like a current source. Here, this guy is simply acting like a current source, and the actual amplification is done by this guy, right? So instead of that, what can you do is to connect these two guys together. So this way you see that amplification is done by what transistor? What is participating in amplification? Both transistors are participating in amplification. Power consumption is same as before. Same structure. Instead of connecting only NMOS to Vin, I connect both of them. So you get the transconductance from both NMOS and PMOS. So it's more power efficient. For the same current, the GM is contributed by both transistors. So the effective GM is twice here. Here you get. So same thing we do here. We connect this NMOS and this PMOS together. Okay. Now that we are in this path, let me just explain some more things. So for the NMOS, we are doing this. In phase 2, we are doing this. In phase 1, we are doing this. So this also, we have a capacitor. In one phase, we do this. In the other phase, we charge it to VDD. And here is where I apply the D. Right? Now if you see here, these two plates are connected to ground. So I can basically connect the two together. Fine. So that will basically result in this simplification. So I'm redrawing the same circuit like this. So in one phase, I am connecting this capacitor to the source of PMOS. Other phase I am charging it to VDD. Fine. I have another capacitor. In one phase I am connecting it to the NMOS, and what should I connect it to the other phase? I should connect it to ground. The same thing I am just redrawing in a different way, that's all, right? This is the same circuit we had for the NMOS, and the top one is for the MOS. Now I will do some hand waving and I will say that I will not go and connect this to ground, I can just do it like this. Now I have two capacitors in series. I can basically put into a single capacitor. So I will draw it in a different page. So we have the same structure. I will replace the two capacitors in series by a single capacitor. So this is connected to VDD in one phase, second phase it's connected. It is the same thing. I had two capacitors connected like this and the center was grounded. Some hand waving I am doing and I will say I am not connected to ground. And the two capacitors in series I replace by single capacitor. Right? So this is good. We can have a single-ended amplifier like this. So if you want to have a differential structure, what should I have? I should have one more copy. So like this. Yeah, I will have the same thing. Okay. VDD and ground. So this is the positive input, negative input. Same thing. But here if you see, this is like having two individual amplifiers and trying to amplify the difference. So that is like taking two common source amplifiers like this and saying that I apply positive input, negative input, it's a differential amplifier. But what issue this has if I do this? Huh? Mismatch, okay, not just mismatch, but if you remember, this is not a differential amplifier, you know, right? What is a differential amplifier, you know? True, but what is the simplest differential amplifier structure you guys know? You have two transistors, yes. Forget about the load side. At the source side, what do? You put a current source. Someone must have seen this in some form or the other. Why are we doing this and not this? Sorry? Not the same current. Yeah, what about? Basically, see, if you think about it, this is responding to both differential and common mode signals. That is, see, you want the circuit to respond only if there is a change in this guy. Okay, that is, if let us say I have the positive input V plus and V minus. If there is a difference in this as delta V by 2 and minus delta V by 2, that is when I want the circuit to respond. If both of them increase to say plus delta and minus plus delta and plus delta, there is no differential change. Individually they are changing by a small amount. Then I don't want the circuit to respond. In this case, it will respond even to common mode changes. But when I put a bias current in common like this, it will reject the common mode thing. Okay, it's okay if you don't remember, but anyways, but that is the issue with this. That is why we try to share one of the bias currents in the two branches. So same issue will happen here also. It will also respond to common mode changes. It will not only respond to differential changes, also to common mode changes. So now take an inspiration from here. So from this circuit, which had a poor common mode performance, what I did, I shared the bias current to improve the common mode. So loosely speaking, what can I do here? I have to share something. What can I share? What is there that is biasing it or doing something? This is the stuff, main transistor. What is the other thing that you can share? Huh? That's the only see, if you think about it, the only thing that is biasing is this capacitor. Right? This capacitor is what is sort of getting charged to the supply and it's getting connected like this. So we don't have a bias current. We just have you can think of it as a bias capacitor. So you can basically share the two to improve the common mode performance. And that is what is done usually.
So we can say that both the parts are sharing that particular.
Yeah. That is similar to sharing the bias current in differential amplifier, very loosely speaking. That is done to simply get common mode performance. So now we have the same capacitor shared between these two guys. So this is charged to VDD and charged to ground in one phase. And of course, this is quite new. I mean, a couple of years back is when people came up with this. And this is called a floating inverter amplifier. It's called a floating inverter structure. I mean, because you can clearly see it's a CMOS inverter. If I have to draw at a symbolic level, I have a CMOS inverter. I am not connecting the supplies to VDD and ground directly. I am actually powering it through a capacitor which is charged to the supply. Right? This is VDD. So what happens? The capacitor is charged to VDD and then we are connecting it to the inverters. I also have the differential half. I am not showing it for simplicity. So initially this is charged to VDD. The CMOS inverter operates with the full supply. As time progresses, we are drawing current from this guy. So what can you say about this voltage? That will decrease. And what will say about this voltage? That will keep increasing. Basically, voltage across this guy will keep reducing. If I look at the individual voltages, I will say V top and V bottom. As you are drawing current from the top plate of the capacitor, V top reduces, V bottom increases. So the overall voltage across the capacitor drops. So the current in the circuit also drops with time. This way you can get a dynamic bias. So as I mentioned, it's only a couple of years old. And I mean, there are other structures of this dynamic amplifier also. I'll just show one and we'll stop. I'll just show the circuit, I'll not go in detail. This is what has been commonly done for quite some time. You apply the inputs. Okay, and before that here, when are we drawing current from the supply? In phase 1, and what are you using that current for? We are only using the current from the supply to charge the capacitor. We are not connecting the supply directly to this guy. So if I draw the clock phase, I mean let's say this is phase 1, phase 2. When are we drawing the current? And how will the current look like? It will look like a delta function and ideally. In practice it will be some kind of. So again, this is a static circuit or a dynamic circuit. It's a dynamic circuit because only when the clock is making the transition, we are using the voltage supply, voltage source to only charge the capacitors, and that is why we are getting a dynamic behavior. Right? So if you want to power the transistor amplifier off, just disable the clock. That's all. Then it will not draw any current. This is much better than having a regular op-amp where you have a bias current always connected. Right? So there is one other dynamic amplifier which has been used, which is this. Again, the idea is you want to have dynamic power, so you should only use the power to charge capacitors, right? Only then you can have some kind of current profile like this. So here you have parasitic capacitors. So this is what is done. I'll directly show the circuit. So here, when clock phase phi is 0, what happens? What happens to this guy? That is off. Then what is on? The top switches are on, and we are using those switches to charge those parasitic capacitors to VDD. So at that point, when clock falls to 0, is when we will draw current, and that current is drawn only to charge those parasitic capacitors. And once the capacitors are charged, when phi is 1, the circuit looks like this. We have the two parasitic capacitors here. And this guy is on. This is, let's say, VDD. So if we apply V1 and V2, what will happen now? This is initially charged to VDD, both of them. So what will happen now? We will start to draw currents. And again, if one of the voltages is greater, say V1 is greater than V2, the left side current will be greater than right side current. We are drawing current from the two outputs. So initially both of them will start at VDD and they will start to drop. So the left side voltage will start to drop faster than the right side one. Now if you see that, if let us say my delta V1 minus V2 is some delta V. Now if I wait long enough, I see that with time, the difference between the output is also increasing, right? And that difference is proportional to difference in V1 and V2, right? Because if V1 was equal to V2, what can you say about the two voltages? Both of them will do this. If one of them is smaller than the other, it will do this. And if the difference is large, if one does this, other will do this, right? So if I look at the voltage at a given time, the difference you get will be proportional to delta V, right? Because if the difference is large, the difference in the slopes will be small. If the input difference is large, the difference in these two output slopes will also be larger. So this way you can also get an amplification. So this is another kind of dynamic amplifier which has been used for quite some time. And this is basically like an open loop integrator, right? Because if you see, we are drawing a current from a capacitor like this. That's what is happening. And this current I1 is dependent on the input, is proportional to V1.
Motivation was just to save power.
That's all. So here again, if you see, the current is drawn only when the clock is going low, and the current is drawn only to charge the capacitors. There is no direct short circuit path from VDD to ground. The moment you have that, then you have a lot of power, and that's what is happening in regular opamps. In regular opamps, you have something like this, right? PMOS will be there and NMOS is there, VIN or something. Or let's say it's both of them are connected here also. You have a direct path. Or even if you have a normal common source where the PMOS is connected to some bias voltage, you always have power consumption drawn from VDD to ground. And the goal here is basically in these switch capacitor circuits, because the current profile is this, we are only interested in charging our load capacitor or feedback capacitor or something. And all the capacitors, the current required is like this. We need maximum current only in the initial phase, and after time progresses, the current required is small. So you also try to follow the same in the op-amp. Okay. Yeah, I will stop here.